Okay, so this is the basic interface of the Hysys software when you open the Hysys. If you don't know how to open the Hysys, let me show it to you. If you click on the start menu and you search for Hysys, you will be able to see ASPEN Hysys. The version that is installed, I have V11, and you just click on it and it will open up the Hysys for you. Now, for the students at KFUPM, I think you cannot use Hysys at your homes. You need to be connected to the KFUPM network because our server is inside the network. So, but you can use it in the library, you can use it in the computer labs in building 3, and you can also use it in the computer lab in the student's home. Okay. Now, when you open ASPEN Hysys, this is the menu you will see. For example, these are what's new means. And for example, you want to learn about the features of Hysys, you can learn from here. There are some example files available with the Hysys software itself. You can click on examples and you will be able to see some examples from here. Like for example, acid gas cleaning, you can open any case file. I'm not opening any now, but for example, here we have like liquid treating, acid cleaning, and many more. Okay. So you have crude ammonia synthesis, CSTR, and all of these things. So the case file means your workbook, or let's say, for example, your simulation case study. Okay. V10 is good. Yeah, V10 is fine. I think in our labs, I think the labs, they are already working on it to install V11. But I think the processes that you are working on, or because you are be working on already established processes, so you don't need to worry about the version really, because the parameters that you need are not that sensitive to the version 11. Definitely it is better than V10 and maybe in some aspects, but I think not really in the areas you will be working on. So now to start a simulation case, for example, any case study, you need to click on new. As you can see it from here, when you click on new, you will get a new case study. Okay. So it's taking a while to open up a new case. And once you open a new case, now this menu is really important for you to understand. First of all, you can see on the left side here that there are some requirements. Okay, it says component, and you can see it's red. Okay, it is underspecified. If you hold the mouse over here, it says it's underspecified. It means you need to specify components. Now, what are the components? The components are basically all the compounds that are used in your process. For example, let's take a simple case of water heating. You are heating water from, let's say, some temperature to higher temperature. Now, in that case, your component should be water. But let's say if you have another case, for example, you are burning, let's say, methane with air. Now, in that case, your components must include all the reactants as well as all the products. So in that case, our components will be methane, and air can be comprised of, let's say, right now we can assume that's only nitrogen and oxygen. So we'll say our components will also contain nitrogen and oxygen. Plus the products are, let's say, CO2 plus water, and if there is any carbon monoxide, we can keep that in component as well. So components are must before we start any simulation case. We need to define the components. Okay, and components are can be added from here. It can be imported or it can be added from here. So when you click on the add button, you will see another menu, and from this menu you will be able to see here all the components. Now there are tons of components here, and you can search your component by writing the name. For example, if I write water, you'll see I can search by name. Okay, or I can search by, let's say, a simulation name, or I can search by formula. So usually this typing the name works better. Like for example, I can search for methanol. So when I write methanol, I can see the compound methanol, its full synonym and its formula. I can search for, let's say, carbon dioxide, for example, or if yeah, it should show up carbon. All right, yes, it shows elemental carbon, but it should also show carbon dioxide. If it is not showing this way, I can search for CO2. I can write like this, the formula here, and it will show up CO2 for me. So any compound that I would like to add can be added here, or those which are in my simulation case. Let's say for now we can add, for example, water. You can add a component by double clicking on it, or when you select it, you can click on add. Like for example, I added water. I can remove it by clicking the remove button. Or if I want to add, so when I search for water, I can double click on this, or I can click on the add button. It will add the water to the component list. Now let's say add another component, for example, here add methanol. So when I search for methanol, I can see it here and add it. I can add any other component. Uh, let's say acetic acid is shown here. Let us say add acetic acid, for example. Okay. Now these are the components. Once you have added the components, don't forget to save your file. So because sometimes Hysys may restart with unknown reasons, so you need to save your file. So I can click on save as, and you can select any appropriate location and then save the file. Now let's say I can give it any name. Now there are different versions to save the file. If you save it as .hsc file, it is the default one. But the problem with this version is that it is not back compatible. For example, if I make a file in V11 and save it as .hsc, I will not be able to run it on V10. Okay, so you can save it as a .hsc file, or if you save it as XML or I think HSCZ, but mainly XML, then you will be able to open it on other version as well. Okay, so the older version as well. So once I have saved the file, now the next important thing after adding the components is to add the fluid package. Now, what is a fluid package? The fluid package is basically thermodynamics relationship, or let's say you can say equation of state, which can calculate the properties of the fluid that, or let's say the properties of the mixture or the components at the given conditions, pressure and temperatures or whatever. So you know, for example, in chemical engineering, let's say when we have a chemical reaction happening, or let's say when there is an energy balance, we need to calculate the enthalpies, for example, at certain temperatures. We need to find other properties, for example, the heat of the reactions, and let's say we need also to find for gases, for example, or liquids, the specific volume. All of these things are basically derived from, you know, the thermodynamics packages that we will be using. So this is really the heart of the process. You know, it's really important to choose the proper thermodynamics package. Otherwise, if you choose a wrong package, you may get some numbers when you are doing the simulation, but those numbers will not be correct, or they will not be accurate. At least the results will not be reliable. So this is really important to choose a proper thermodynamics package. Now I can click on add again here, just like the components, I can click on add and I will add a thermodynamics package. From here, there are many packages. If you can see, these are specialized packages for acid gas, you know, treating or acid gas treatment. Okay. And there is, you know, Antoine's equation of state or Newton's law, which basically relates, you may be well aware of that, which relates the vapor pressure to the temperature through certain coefficients, A, B, and C. There are some other common equation of state, maybe you have heard their name, like for example, Peng-Robinson or NRTL. I'll talk about this error later on, like NRTL, for example, or many others.
SRK, Doctor.
Yes, SRK. So how to choose a proper fluid package? Now there are certain, you know, heuristics about that. There are certain, let's say, guidelines to choose a proper fluid package. There is a slide I'll share it with you now. I found online. You might find other materials also. This is from this author Terry Ehring, and it's for ASPEN tutorial. I removed other slides, but I kept the slides about how to choose a thermodynamics package. Okay. So the first question that we are going to ask ourselves about the package, about our components, like do we have any polar or non-polar compounds? So if we have polar, what do we need to do? If we have non-polar, what do we need to do? And our system pressure, if it is less than 10 atmosphere, then we know that our system will be mostly behaving ideally, or at least we are safe to assume the ideal relationship. But if the pressure is greater than 10 atmosphere, which is in most of the cases, then we cannot assume anything ideal. Okay. And are there any interaction parameters available to us? For example, if you have a mixture of component, let's say water and ethanol, or let's say any other, let's say water with some electrolyte or any other organic mixture, do the components have any interaction with each other? If yes, yes, most probably they will have. So what are the interaction parameters? We need to provide that. If we have that, it will also make our choice easier. So this is one of the flow sheet or flow diagram to if your components are polar or non-polar. If they are polar, then let's say if there is any electrolyte in your components, if there is an electrolyte, you may go with NRTL, okay, or Pfizer. If there is no electrolyte, maybe we need to see figure 2, okay. If they are all non-polar, then they are real or pseudo components. Real means real components are those which are already in Hysys data bank, okay. Sometimes you may have a component which is not really available in Hysys. You can add pseudo components, and you can have like certain properties of the compound. Let's say you synthesize a new compound and you want to use that in Hysys simulation. Now in Hysys data banks, there are no properties for that component that you synthesize newly. Now you can add that as a pseudo or a component, and that for that component you need to add certain properties. Let's say it's temperature, let's say it's boiling point or whatever properties Hysys require. You can add a pseudo component. So if it's a real component and this non-polar, Peng-Robinson or RK sub or Lee Kessler will work fine for you. However, if it's a pseudo component, then is it again? We need to ask about polarity. So then we need to choose either of these equations. In your case, mostly you are going to work with the real components. However, you need to see if they are polar or non-polar. Okay. If there are electrolytes, you need to go with NRTL, otherwise Peng-Robinson. If there is non-electrolyte and they are polar, then we can polar non-electrolyte. If the pressure is greater than 10 bar, you need to go with SRK, Peng-Robinson, or these. Or if that is if the interaction parameters are available. Okay. If they are not available, then you can go with the modified SRK or other equation. Similarly, if the pressure is less than 10 bar and the interaction parameter are available, then it is LL means liquid. Okay. I think then in that case, let me just try again. So you can go with NRTL or UNIQUAC in that case. If not, if then you need to go with Wilson or UNIQUAC and their variances. And similarly, so on. If you don't know the interaction parameters and then there is a liquid, then you need to go with UNIFAC, LLE, liquid equilibrium data, or let's say if there is no, then you need to go with UNIFAC and its extension. So it's like a flow chart, and you need to see your compounds that you are working with and pass it through, or let's say test it through this flow sheet, and then you will be able to come up with some good choice. Okay. Similarly, if you go to figure 3, basically, does it show here figure 3? No. So let's say if you have if you are using Wilson, NRTL, UNIQUAC, or UNIFAC, in that case, do you have okay? This mainly works with in case you have polymerization or something, but still, if you have vapors, if yes, do we have any polymer product like hexamer or dimers? Then we'll go with these conditions in this equation of state. If no, then we'll go with Wilson, NRTL, or UNIQUAC. So this is a quite detailed one. There is another one which is called Bob Cedars recommendation, and it's a little bit shorter one. Like for example, if you have hydrocarbons, then yes, then if it is LG means light gases. If there are light gases, yes. If they are polar, organic polar compound, if they are yes, then you can go with Peng-Robinson SRK. This is a modified equation. If no, then we'll go to figure 5. If they are liquid or if they are light gases and they are not polar, okay, then sorry, if they are not light gases and they are polar, then we'll go to figure 6. We'll go to next figure 5 and 6 in next phase. Okay. Similarly, if you have hydrocarbons, sorry, if they are not hydrocarbons, then if they are electrolytes, then you'll go with NRTL, and if they are not electrolytes, then we'll go with sour water, NH3, or aqueous amine solution, or any other specialized equation of state. So figure 5, if it is here, figure 4, then we have figure 5. And if it is hydrocarbon and or light gases, then If we know the boiling point range of the compound, if it is narrow, then we'll go with this case. If it is very wide, then we'll go with the leakage curve. Okay. And P means P stands for the pressure region, T stands for the temperature region. And all of these factors will help you decide about these things. Now, similarly, if we go back and see figure 6 here, if they are not light gases and there are some polar or non-polar, in that case again we will see BIP stands for the binding interaction parameter. If the binding interaction parameters are available, then we will go with the okay, if there is phase splitting or no. So it's really detailed flow chart. So you need to look at your components, and then based on this you're going to decide your equation of state. There is also recommendation table from Hysys itself. This is called hypertech recommendation. So for example, if you are using a TG dehydration, the type of system, then you can use Peng-Robinson. If you have sour water, then PR will work. PR stands for Peng-Robinson. The cryogenics, PR and PRSV, air separation. So you can also go through it, and it will provide you a suitable recommendation. Now, so that's why when I was working on with this case file and I click on Peng-Robinson, basically Hysys pops up an error message, and it says to me that it is not recommended. Why? Because of the acetic acid. Okay, and Peng-Robinson will not work. So either I need to delete the component or I need to change to another equation of state. Okay, there is also a method assistant in Hysys. Okay, and let me just okay, after this I'll show it to you. So you can also use the method assistant in Hysys to work to try to choose the equation of state for you. So Peng-Robinson will not work in this case. Sorry. NRTL is also NRTL will work fine. NBS is for the steam, so it will not work definitely. However, NRTL is working fine. You can choose NRTL as your equation of state. So how to choose an equation of state? You can double click on it, and it will add the equation of state. So you see, I can see the basis, and now this basis is already added. Now sometimes I may need to use more than one equation of state. Okay, so I can click on the fluid. I can come back to the fluid package, and I can click add another one. Like for example, you may have multiple components, and for let's say for one set of components you may want to use one equation of state, and for other set of components you may want to use another equation of state. So you can click on add another basis, and now in this case for you can choose another equation of state. Let's say we can put Peng-Robinson PWV, or let's say sour PR. I hope it will work. Yes. So sour Peng-Robinson or sour SRK. So we can add any of these equation of state. Let's say add sour SR. So this is my basis too. You can rename the basis. Like for example, I can rename it to an RTL, so that at least I can remember in my simulation study later on. An RTL, and let's say here I can rename it to sour SRK. Are you guys with me?
Yes, Doctor.
Okay, great. Let me see. I have some questions. Let me check that in the chat. Okay, so let me go through the questions. Does the package include SAFT? Yes, we have. I think SAFT. If not in ASPEN, I think in if not in Hysys, in that we have. And ASPEN Plus we have, I think. What if I had a mixture of polar and non-polar? Yes, this is what I said. You can add, let's say, in that case, if it is a mixture, then you need to do a thorough search and try to find out maybe there is something information available in the literature, or maybe if they are not, if you have the interaction parameter, I think you can then go with the NRTL or this set of equations. So pseudo means a user constructed mixture. No, not a mixture. Pseudo means a user constructed component in the Hysys. I'll show you in a while. Okay. How can you tell if the gases are heavy? You can tell from the, you can like, it's, there's no fixed rule, but let's say, for example, light always means, like, for example, from C1 to let's say C5, or even up to C10, but other than that you can term them as heavy. How does the program determine the which components uses which bases? Yeah, we'll see that later on, and in the simulation I'll show you. So coming back to one of the questions related to components. Now these are real components because all of the components are available in the Hysys. Okay. If it is not available, then there is a way to define a pseudo component in the Hysys. You see there are pure components. These are hypothetical. So if it is a hypothetical component, then in that case you need to add a component. We will not go into details, but you can add a component here. You can put the initial boiling point, all of these things. There are some parameters which you need to provide, and it will create a component for you, and then it can you can work on it in the simulation. Okay. But a majority of the components they are already there, and like, for example, the hydrocarbons and a lot of these things are already available in the uh, component in the data bank. So all the components, which means the pure, and they are here in the data bank. Basically, Hysys has a data bank and it contains all the properties. And if, for example, for ethane, all its properties are there already available with the Hysys. Okay, its formula, molecular weight, and other parameters are already available with the Hysys. So this is these are equation of state. Later on, I'll show you how we can use a specific equation of state fluid basis to use it for the simulation. Now, if you are working with petroleum assay, like, for example, you have a crude mixture, then in that case you can define your assay here. But we are not working with that. But you can define petroleum, let's say, a crude assay here, and you can add its properties, and you can work with the crudes also. There's another important information that we need to add here. If there is any chemical reaction in our process, then we need to add the reactions here. Okay. We'll try to do an example with the reaction, but quickly I can show you, like, just like the previous one, we can need to click on the add button and it will add a reaction set. Okay. So once we add a reaction set, then we once this is like a reaction set. Okay, you can see it here. I have a set one here. Now you can add a reaction here by clicking add a reaction button, or by clicking the small button. I can say I can click on new reaction. New reaction is what I'll add myself. There is some existing reaction, but with the components that I choose, there are no existing reactions. I can click on add a reaction, for example. Now, when I click on add the reaction, there are different type of reactions that I can add in Hysys. Conversion reaction, the first one. Conversion reaction is very simple. You need to specify the stoichiometric coefficients, like, for example, hydrogen plus oxygen will give you water, or let's say any reaction that you have. So when you click on the conversion reaction, you click add reaction, for example. So it added reaction one. Now reaction one I can add, and then I'll add the components here. Right now I don't have any chemical reaction, but let's say I can add, let's say, the components, and all these things. Now I can add a stoichiometric coefficient. For the reactant, it should be negative. For the products, it should be positive, and the component the reaction should be balanced. Okay. After that is balanced, I can add here the base component, and I need to define a conversion. So I'll add one of the component, let's say methanol, and then I'll say the reaction phase, is it overall or vapor phase or liquid phase. So usually it is overall for case studies, but these information are available with the problem statement, or maybe you need to find it out yourself. And then you need to add the conversion, like, for example, it is 50% conversion or 60% conversion, or whatever. You need to add the whatever value you have available, you need to add the conversion. Okay. So once this information is added, you can and the reaction is defined, then you need to click on attach to fluid package. Okay, it is important, otherwise you cannot use the reaction set. Similarly, if you click on, you can add multiple reaction, like, for example, I have one conversion reaction, I can have one equilibrium reaction. So when you click on equilibrium reaction, it will add another one. Let's Okay, it will not allow me to add another reaction right now because I have one reaction that is incomplete. So let me delete this. Delete reaction. And I'll click add a reaction, and let's say I choose equilibrium one. Now it has added an equilibrium reaction, and I can double click on it to open the configuration menu. Again, in the equilibrium reaction, I need to add the components, like, for example, let's say that all the reactants and the products. and then specify their stoichiometric coefficient, reactants negative, products positive, and I can define the K equilibrium. Okay, I can define the K equilibrium from data if I have the data available. Okay, with the time temperature, like for example, K equilibrium was stable, I can define the temperature and the K equilibrium. Okay, all these things, or I can allow it to calculate from the Gibbs using the Gibbs free energy. Okay, there are also library of reaction for equilibrium reaction, like for example, the water gas shift reaction or ethyl benzene to styrene and hydrogen. Okay, these equilibrium reactions are already available. You can use them and add to your library. Okay. Similarly, there are other. We'll do some examples later on, but right now, if you have a kinetic reaction or a heterogeneous, if you have a kinetic reaction, you need to provide the kinetic information in this case. For example, the components, and you need to provide the let's say the best component, the reaction phase, and most importantly, you need to provide the activation energy and the frequency factor for the reaction. Okay, if based on that, Hysys will basically calculate the temperature dependence of the frequency or the reaction rate constant. Okay, so once you have whatever system you have, once you have defined the reaction, then you need to click on add to the fluid package, and it will be attached to the fluid package. Right now, let us say we don't have any reaction. I'll just delete this. And okay, now once you are done with the components and the fluid package and any chemical reaction, if you have, you can click on you can go from properties environment to simulation environment. I'll just click on simulation, and it will take me to the simulation environment. Now inside the simulation environment, you have here, this is called the model platelet. It contains all the unit operations that we can use in Hysys. For example, we have a mixer, we have a tea or a splitter, we have a cooler, heater, we have a cooler, heat exchanger, pump, valve, a lot of other. We can go to let's say heat transfer. For example, these are the heat transfer equipment. We can go to the reactor. We have the CSTR, we have a plug flow reactor, we have a conversion reactor, we have Gibbs reactor, we have equilibrium reactor. So depending upon the nature of your chemical reaction, you need to choose the type of reactor. We have separators. In separators, we have normal separator, which or you can say a flash separator, three-phase separator. When you have more than one phase, and then you can separate them in multiple streams. We can have the distillation column, different types of columns. Okay, and pressure changes means pump, compressors, and turbines. These are the manipulators. We'll show you. For example, you can have a recycle stream. So these units will help you convert a recycle stream. Okay, spreadsheets to relate a parameter of one stream to another, or add some calculations to the streams. Adjust means you want to adjust the streams, or let's say adjust two streams to certain ratio. Okay, and here we have set. Set means you can set your objective of one stream. For example, I want to achieve a temperature, let's say certain temperature, by varying another parameters. All of these things we can do through these unit operations. We'll go through them one by one. So here, let me save the file. You can save this. You can click this icon, or you can press Ctrl S. Before starting, regarding the unit sets, right now we have the default as SI units. You can change to field units, or you can change to, let's say, euro, or you can go to user units. Okay, user defined or custom units. Okay, and you can click on the unit sets. Now this is a custom defined unit set, and you can change units. Like for example, for angle it is degrees here. I can change it to radians, and it depends on your. But the units are really they are not any there is no inconvenience in the units. So you can put data in multiple units. However, you will get the answers, or the in the flow sheets you'll get the answers in the unit set that you are using, or the default one. Okay. So you can create your own unit sets, or you can use the default one. Let us keep it to SI, and that's it. Similarly, here on the top, you can see here the active button. This is basically the Hysys solver. Okay, it is active means any information that you will put in the Hysys simulation case, Hysys will process the information. However, if it is on hold, then it means any information that you put, it will be entered into Hysys, but Hysys will not do any calculations. So this is really important to keep an eye on this, because sometimes when you are doing the simulations, you come up with you receive a consistency error or any other issue. Due to an error, this solver goes on hold. Okay, and then you try to correct your information or rectify the error. You try to delete what wrong information you provided, but still it is not solving. So this is really important to have a look on or keep an eye on the Hysys solver, that it must be active to work properly and do the calculations. Here we have in the object platelet, we have two types of streams. One is called the material stream, the blue one, and the red one is known as the energy stream. So material stream is for, as the name indicates, for anything material. It will be a single component, a mixture, or whatever. So it is a material stream. Energy stream is the heat that is required by, let's say, if you have a heater, it needs an energy stream. If you have a cooler, it needs an energy stream, but in that case, it should be a coolant. Or let's say if you have a reactor, it may need a heat duty or something, you can provide it by using the energy stream. Okay, clear? Are you with me?
Yes, yes. Fair.
Yes, doctor.
We have a question, let me check. Okay, can I create my own mixture rather than components? You can create your components and then you can create your mixture inside the simulation environment. You can have a component as a type of mixture also, but in that case, for that mixture, you need the properties for that mixture, any experimental data, not theoretical data, for Hysys to be able to predict its other properties. Okay. So let us start by, so this is our simulation environment here. You can see this is the flow sheet and the main window. And I can add a material stream. The way to do it is you click on material stream, and then when you bring the mouse or the arrow to the flow sheet area, you will see a plus button and you can click on it. It will add a material stream. Okay. Now the material stream, if you look here, Hysys name it as, by default as 1. Okay. And it is light blue. Now this light blue means that this information about this stream is not complete, and it is not yet, or you can say it is not yet solved. Okay. When I double click on the stream, I can provide the information. When you click on the material stream, double click, sorry, you will see another pop-up menu. And here I need to provide the information about the material or about the stream. So you can see here, Hysys will guide you from, by giving you flashes. Let's say here it says unknown composition, and you can click on it here on the composition from the left tab, and you will see the composition. Now you see all the components that I added are here. Okay, so I added, you remember I added water, methanol, and acetic acid. Okay, so you can click on composition, and the composition you can click on the added button here. You can you have the options to provide the composition either in mole fraction for a stream, let's say in mass fraction, in mole flows, mass flow, or liquid volume flow. Okay, so it's depending upon the data. Let's say we keep it default to the mole fraction, and let us try to create a stream. Let's say we keep the water as 0.5, methanol as 0.2, 0.20, let's say. Now the remaining, I know it should be 0.3 as acetic acid, or I can click on equalize. Oh, okay. If I click on equalize, then it will basically equalize all the composition to 1. Okay. But if I click on, let's say, if I do it, if we have two components, then we can click on the normalize button. Let us put the composition by assumption. Let's say 0.5 we have, and 0.2 methanol, and 0.3 the acetic acid. Okay. And I click on OK. The total should be 1 because small fraction. And I click on OK. Now, once I have defined the composition, it says to me unknown temperature. I can come back to the conditions. Now here you need to think about degree of freedom here. In this case, if you look, we have 2 degrees of freedom. Okay, we need to define the pressure and the temperature of the stream, and Hysys will be able to simulate the stream, or let's say solve the stream. So we need to define either the temperature here or the pressure here, or we need to define if we have a saturation condition. For example, if our stream is either saturated liquid or saturated vapor, then in that case our degree of freedom is 1, and we need to define either the pressure or the temperature. Okay, so let us start now by, for example, defining the temperature and pressure. Let us say our temperature is, for example, 55 degrees Celsius. So if I write 55 here, okay, you will see on the right side, I can choose the units. And if, for example, I can choose centigrade, Kelvin, Fahrenheit, or Rankine, whatever. Right now, my units are, I say Celsius, so I can put C. Let us put the pressure as, for example, 2 bar. So when I press 2, the default unit of SI unit for pressure is kPa, kilopascal. And I can click on the small arrow and I can choose the units that I have. Let us say that these units are in bar, so I can go and search for bar, and I can put the pressure as 2 bar. Now Hysys shall be able to solve it, but we need to provide a flow rate, okay, unknown flow rate. So let us say we put as the default as 100 kg mole per hour, or you can choose any other units, for example, for the flow rates as you have. Let us keep it 100. As soon as I enter 100, all the information, you see the ribbon has turned green now, and it says okay, or the stream is now solved. And you can see that Hysys calculated the mass flow rate, the enthalpy, the entropy, and even you can go to the other properties. For example, click on the properties tab, and for this mixture, you can go and see all the properties that you need. For example, the Cp by Cv, the Cv value, the viscosity, the bubble point. But all of these are calculated based on NRTL. You see the fluid package. This is NRTL. We choose NRTL. I can change it to SRK. And we can see, let us do a quick survey here. For example, we can see the molar volume or the specific volume of this mixture. We can go to properties and we can search for the molar volume and see if we use a different equation of state, what happens to the molar volume. The molar volume here right now is 3.547 in 10 to the power minus 2. And if I change the fluid package, and let us see the molar volume again. So it is 3.553, and before it was 3.547, almost 3.55, but there is a minor change. So you see, when you change the equation of state, your answers or your calculations will be affected by the equation of state, by the choice of the equation of state. Okay. So now this stream is, if I close this, let me save it, and if I see this, if I look at the stream now, it has turned to dark blue, which means the stream has been solved or simulated. I can also rename the stream. For example, I can the default name is 1. I can call it anything. Let's say I call it S1 or whatever. It is shown here. Okay. Now this is my stream number 1. Let us say if I have another stream, for example, I can add any other material stream. Let's say I add. Okay, let me do another thing. Let me decrease the water fraction here. Go to composition and let's say 0.1, and let's say make this one as 0.5. and make this one as 0.4, and I want to add more water to it. And you'll notice that when I change the composition, the properties will change. You can go to the properties again. Let's say look at the specific volume again. Hysys, in Hysys it is known as molar volume, and you see it became 4.673 because I changed the composition. Now let us say add another. Let's say we call it stream number 2, and let's say it is pure water. Okay, and I want to mix these two streams. Okay, so I add another stream. Now I go to the composition and I click on edit, and let us choose mole fraction of water as 1. This is pure water, and click OK. Now I go to the properties. Now in that case, in this case again, I need to provide these conditions. The conditions, the temperature and the pressure. Let us say we add here that it is the liquid mole fraction or the vapor phase fraction is 0. 0 means it is saturated liquid. Okay, there is no vapors. You see the vapor phase fraction is 0 means there is no vapor or saturated liquid. If I put it as 1, it means it is saturated vapor and there is no liquid. So let us put it as 0. I want to put saturated liquid. Now in this case, I need only the pressure or the temperature. Let's say if I put the pressure as 1 bar, or let's say 1 atmosphere, you will see the value Hysys calculated 100. We know that at atmospheric pressure, the boiling point of water is 100, right? And you see Hysys calculated the temperature for you by 100. If I change the pressure to 2 bar or 2 atmosphere, for example, you will see that this value will change. You see that the temperature, the boiling point of water at 2 atmosphere is 120.7. And if I provide the molar flow rate, let's say I provide the mass flow rate, for example, uh, 15 kg per hour, for example, any value. Now this stream is solved again, and the molar flow rate is 0.8 kg per hour. Let's say increase it a little bit to 25. Okay. Similarly, if I change the vapor phase fraction to 1, now it will be saturated vapor. However, the boiling since it is, as I told you, saturation line, the temperature is constant. You need to add the latent heat of vaporization, or you need to remove the latent heat of vaporization for condensation. So the temperature is going to be the same. Let us say for now we put it as 0, and we say that at this condition we have the saturated water. And let us change the pressure back to 1 atmosphere. Okay. So do you guys understand this point? So we need to define either the pressure and the temperature, or if we are at saturation condition, then we can define our system by defining the vapor phase fraction, and we can define it either by the pressure or by the temperature. Now there is another thing you need to pay attention in Hysys. The blue text is the information that we add to Hysys, and the black one is the one that is calculated by Hysys itself. Okay, so we cannot change the black one. You can see, you can click on the, you cannot edit it, but you can, when you double click on the blue one, you can change it. Okay, so you can change the blue information. Like for example, I can make it 30, but I cannot change the information that is in the black one because it is calculated by Hysys. I can close this stream now, and I have two streams. One is called S1, one is called S2. I can drag them here and there depending on my interest. I can rearrange it. Let us say we are mixing. We want to mix these two streams. So I can click on the mixer and add it here. Now you can see it from the icon that the mixer basically takes in multiple streams and gives you one outlet stream. Now with the mixer, the default name is mix 100. I can double click on it, and the first thing for any unit operation that I need to do is to add the streams, the required streams. For a mixer, there should be at least 2 input streams. Now the inlet stream, I can click on the arrow and I can choose any of the available streams. Like for example, S1 is available. I can, and when I click S1, you see it goes into the mixer. Similarly, I can click on S2 water. Now these two, so minimum 2, and I can add even more. If the stream is not available, I can create a stream from here by typing. For example, we don't have any stream for the outlet, you see, but I can create a stream from here, right here. I would say, let me call it mixed. Okay, mixed. Let's say call it S3, stream number 3, and mixed. Okay, and as soon as I create it, let's say, you see it is mixed automatically. I need to press the enter, or I can just click outside and it will create, it will mix the streams. Okay, now you can see this again. The mixer, it does not require any other information, so it is solved automatically and it's turned blue. So S3 mix is available now. You can see the information by double click on this stream, or you can double click on the mixer itself. Okay, and you can go to the, for example, you can change the parameters if you have any for other unit operation. For mixer, we don't have any. You can click on the worksheet and you can see, for example, we have S1 and S2 going in. The temperature for S1 is 55, S2 is 100, and the mixture has 55 degree, 55.53, slightly increased. Okay, the pressure is decreased for the average to 101.3, and the flow rate, if you look at the change in temperature, it's very small because we are using very small amount of water. And if, for example, the total molar flow rate was 100, and with the addition of water, it become 101.7, and that's why we don't have any change in the temperature. Okay, if I change, I can change the streams information from here, or I can double click on here and I can change it in the worksheet. Like for example, if I make this as 65, this is the flow rate of water, kg per hour, and you will see that the calculations will change. You see this temperature increase, the molar flow rate increase, all of these things. Let us make it 120, and you will see, because this stream is at higher temperature, it's going to increase the temperature. Okay, let's make it 200. So you see the temperature is increasing. If I change this flow rate to 50, for example, I'll change all the calculations. So you can change the information for the streams from here also. Now we have this mixer stream available. Okay, and let us say try to add another unit operation to it, and for example we can add a heater here. Okay, and this is a cooler, we can add a heater. Okay, and try to heat this. Now when you click on the heater, again you see it is red. Red means that the streams are not defined. Okay, so when we define the stream but it is not yet solved, then it will be yellow. Okay, and you will see it now. Now when I double click on the heater, you'll see here that I need to define the inlet and the outlet, and I need to define either the energy or I need to define the exit temperature, because Hysys needs to and at least one of this information in order to calculate the other one. So if you provide the exit temperature, then in that case Hysys will give you the duty. If you provide the duty, it will give you the estimated outlet temperature. Let us say we put the S3 mix as the input. So you see when I select S3 mix, it will connect it to the heater. I can click on here and I create another one, S3, or let's say S4 heat. For example, you can create any name, and the energy stream, let's say we can create an energy stream, we can call it Qn for example for now, but we don't provide any value. Now the next thing, if you need to provide, you need to provide here is by going to the parameters and need to provide delta P. Okay, delta P is the pressure drop in the heat exchangers or the heaters or the coolers. The pressure drop is really important. Okay, so you can there is always a pressure drop, and let's say for example now we keep it as 10 kilopascal. There's a pressure drop, or you can keep it even zero if you don't want to add any pressure drop. You can keep it zero. Okay, so the pressure drop I keep it as 10 kPa, and now I need to provide either the delta T or I need to provide the duty. So let us say for example, or I can do it here from the worksheet. For example, the vapor fraction here was 0 for the S3 mix. Let's say I want to make it 1. Let's say for example I want to make it saturated vapor. Okay, when I click on 1, it will automatically solve this, and at 93.75 this mixture will be basically saturated vapor. Okay, and Hysys solve this condition, and it will provide us the heat duty. You can, when you click on this here, it will give you the heat duty is 2.170 kilojoules per hour, or I can right click on here and I can add this information, show table, and it will show the information for that heater here. The feed temperature was 61.9. I can delete this also, or if I want, instead let's say I can delete this information. I don't want it vapor. Let's say I want to achieve a certain temperature. Let's say I want to keep it at, for example, 90 degrees. Okay, so again at 90 degrees it will give me some calculations and the heat duty.
Doctor,
Yes,
in terms of delta pressure, so you put 10 delta P, right?
yes, yes,
Before it enters the heater,
yes,
it's at 1 ATM,
yes.
correct?
Yeah, you can see it here. The pressure before it entering was 101.3, and when I decreased it by 10 kilopascal, so you can see the unit here,
Oh,
it
okay.
was 101.3 kilopascal, and now it is 91.32 kilopascal. It is
And that's based on what we want, not.
yes, yes. This is our this is
Okay.
this is the information we must provide to Hysys.
Okay, thank you.
Parameters and change it. If I change it to 0, you'll see sorry, you will see there is no change in the pressure.
No change in the pressure, but it will still heat, right?
Yeah,
Provide
definitely,
heat.
definitely it will heat. So let us
Okay, thank you.
10 kilopascal, and yes, you see with the pressure drop, your duty is also affecting. And when I make it the pressure drop is 0, the heat duty will be 1.37 something kilojoules per hour, and when I make it 10 kilopascal, it will be 1.37. It's the same, I believe. Okay, I thought it's changing. Yeah, it is changing. Yes, it becomes 1.71, so it needs more heat. Okay, so similarly we can add a cooler, for example, and then do let's say cooling, and for that case we will have a cooling duty to cool down this to certain temperature. We can also add a separator, for example, and let's say here we have a separator. We can connect a flash separator, a V100 double, and we can again, when I double click on the separator, first of all I need to provide the connections. So when I add the connection, let's say this is my S4 heated and I want to flash separate it, and I'll, let's say S5 dash vapor, and let's say we call it S6 dash liquid. So as soon as I connect it, it will solve the flash separator for me. I can also add any conversion reaction that I have to separator, but in this case we don't have any reactions. So now basically Hysys will separate this mixture into vapor and liquid, okay? And we have the flow rate of at this condition we have some liquid stream, and the liquid stream we can see it from the worksheet. For example, if I go to the worksheet, we can see that we get around at 90 degrees we get some liquid product, and it will the molar flow rate for that is 14, and the molar flow rate for the vapor product is 46. And we can go to the properties and see the we can see the composition. And for example, the liquid will mainly contain 0.37 water, 0.19 2 as methanol and acetic acid, and so and so. Okay, so you can separate it. In addition to that, you can also let's say add other unit operation. For example, we don't have here we cannot add a distillation, but let us say we can add a distillation column. The next one we can create another stream. Let me just, I can select all of it and drag it here. Let's say we add water methanol stream and we want to separate it. Okay, so I can click another stream, and let's say I call it S1 for separation. Okay, and I go to the composition, and let's say we add a mixture of ethanol and water, methanol and water. For example, let's say we add the water as 85 mole fraction, and let's say we add methanol as 0.15 15 mole fraction, and there is no acetic acid, and click OK. Just keep it simply binary mixture, and in the conditions, let us say put the temperature as 75, or let's say 60, and the pressure as 1 atmosphere or 1 bar. Okay, and the flow rate we can keep it. Just give me a second, please. Okay, so let us put a flow rate of, let's say, 150 kg/mole per hour, and I'm just putting random values. Okay, so now we have a mixture of, let's say, methanol and water, and I want to separate it. Now then this, if I go to the separation column, separators, let me say it's fine. I can have columns. Let's say first one is the shortcut column. Okay, the most important one. You can see here the shortcut column. I can drag. The shortcut column is basically the basic distillation column, which will give you the initial estimates, okay, and the minimum reflux ratio required for your separation. And if, for example, let's say I want to separate this mixture, and I want a certain amount of methanol in the top and certain amount of water in the bottom, okay, certain specification. But I don't have any idea about the minimum number of stages that are required or the minimum reflux ratio. So I'll just try to use the shortcut column to give me these initial estimates. And once I have these initial estimates, then I can go to the rigorous column and design a detailed column. Okay, so this is a shortcut distillation column, and I can double click on it, and you'll see a menu. Again, I'll use the S1 separation as my stream. Okay, the condenser duty, if you have any, otherwise the distillate, I can create another stream called distillate. Then I can connect another stream called bottom, and let's say I can call it QC, and let's say I Q boil. You are with me on this, creating these streams, right? So once you just type in, you will be creating streams. See, the streams are already created. Okay. Now I can click on the parameters tab, and I need to provide the key components. Okay. So what are now, if the mixture, this is a very simple example. In this case, methanol will be our light key, and water will be our heavy key. So what is the light key in the bottom? It is basically methanol. And what is the heavy key in the distillate is basically water. So let's say in the bottom, I want only, let's say 0.05% methanol, for example. And in the top, let's say I want 0.03% water. Okay. And I can provide the condenser pressure. For example, if there is any pressure drop, let's say I put the condenser as 90 kPa, just a random value. If there is any pressure drop, you can just roughly calculate it, because you know the column pressure and the pressure drop, you get the condenser pressure. And let's say the condenser pressure is the reboiler pressure is the same, or I can put it the same as 1 atmosphere. Now you see Hysys already calculated for me the minimum reflux ratio. This is the reflux ratio that will be required in order to get this separation. This much of methanol, let's say 95% for water, and the other for the methanol. We can provide the reflux ratio, and it will give us a number of stages. Now we know that from your separation course that the reflux ratio should be 1.3 to 1.5 times the R minimum. So we can say that 1.3 times 1, let's say the minimum reflux ratio is 1.726. So 1.726 multiplied by, let's say, 1.3. So you get 2.24. Let us put as 2.3, for example. So if I put the reflux ratio as 2.3, Hysys has solved this, and it has given me the, if I go to the worksheet, or let's say to the performance, you can see from here that I have I need the minimum number of trays 4.17. I need the actual number of trays is 9, and the optimal feed stage is 6.59, and the reboiler duty, the condenser duty, all of these are available for me. Now I can use this information to design a rigorous column. Okay. More importantly, if I change this parameter, let's say if I make it 0.005, for example, you'll see that my calculation will change. If I go to the performance, now I need 11 number of stages. Okay, and the optimal feed stage will be 5. Similarly, if I change this to 0.002, I go to performance, I need actual minimum number of stages 7 and actual number of stages 16, while the optimal feed stage in this case will be 12. And also my minimum reflux ratio will be changing here. So it is 1.8 now. Let me change this reflux to 2.8, for example, 2.9. So now in this case, if you look at the performance, you will see my stages from 16, 17 has decreased to 12.9. And you know that when we increase the reflux ratio, our number of stages are decreased. However, we may increase our reboiler duty. If we increase the reflux ratio, we need to increase the diameter, as well as we need to increase the reboiler duty. So let us close this now, and we can use this information to design a rigorous distillation column or detailed column. Okay, so I close this. I'll keep it here. Okay. I think I can copy and paste the stream also. You see, I copied stream separation 1, and the same stream I pasted it. So I'm using it for a distillation column. So for the distillation column, I can choose there are other specific distillation column also, but we'll use this one, the distillation column proper one. And when I add this column, you'll see that I need again P101. I double click on it, and I need to provide the streams. For example, the first information I'll provide as S1 separation 2. This is our stream. Now I need to provide the inlet stage. So the stage from shortcut distillation column, it was at 9.7. So we can choose stage number 9 or 10 as our feed stage, and the total number of stages are 13. can put 13 here, the total number of stages. Okay, and there is no sideways streams, but we have the reboiler. So let's say B is Q or B2, and let's say condenser stream, you put QC2. This is the condenser duty. Okay, you need to specify if you have a, a partial reflux or a total. You have a total condenser, or if you have a partial, how much is your overhead product. Okay, so let's say we call it and let's say, or if you make it a total one, let's see, let's say make it as a total condenser instead of a partial condenser. And if it is a full reflux, then in that case you will not have any. So let us make it a total condenser, and let's say we call it this. Okay. Now once I have done this, okay, I need to the bottom. We need a bottom stream also. So all the information on this is complete now. I can click the next button. It is activated now, and I can go to the next step. In the next step, there are some information about the reboiler type. Like for example, if it is one through with a circulation or other, usually we keep it the default regular Hysys boiler. If you have a specific heater or the information available for you, you can use them. But usually it is the default version that we keep it in simulation file, and we can click next. The next one again is asking the condenser pressure. So let us put it as 90 kPa, and or you can put the condenser pressure, or you can put the condenser pressure drop. Okay. Similarly, the reboiler pressure, let us put as 1 atm, and click next. So it's asking for the temperature estimates of the condenser and the reboiler. That temperature estimate will basically help you in converging the simulation, because Hysys will try to solve it numerically and find a solution to the problem. However, if there is not enough estimates available, then system will not convert. So we can click, if you have any estimates, you can provide it here. Otherwise, it is not a mandatory thing, and you can just click on next. If you have any reflux ratio, we can provide the reflux ratio as 2.9. Otherwise, we can click on done. Okay. So when you click on done, still you may notice that the simulation is unconverged. Okay. Unconverged means we still need to add some information, or the information that we have is not available. So in that case, we can click on the monitor tab, okay, and provide some other information. Okay, when you go to the monitor tab, let me just show it to you again. When you double click on it now, it will not take you to the start menu. It will show you the information that we provided already, and we can click from the left side on the monitor tab. And here we have some specification, like for example, you look here that we have the reflex ratio as active tab. Okay, it is used. However, we need to provide any of these specification. And for example, either the reflux rate or the bottom product rate or the distillate rate, one of it must be provided. Even if none of these is available, you can click on add spec, and let's say you can add another specification. And for example, column component mole fraction, or column component recovery, or column duty, for example, or reboiler duty, or any of these things, or any stream specification. You just need any other information to basically give it a start and solve the problem. Let's say, for example, if you click on column component recovery, or let's say common component column component fraction, then you can basically define the mole fraction of the component at any of these stages, in the reboiler, for example, or in the first stage or second stage. And you need to show a small fraction for the liquid or the vapor, and you can add the value. Okay, so this will solve. Or you can provide a distillate rate. Let us say, for example, let me see how much did we put here, the value for feed flow rate. The feed flow rate is around 150 kilomole per hour. Okay, so let us put the distillate as, go to the monitor, and let us put the just try to put it as, let's say, for example, the 50 kilomole per hour. Okay, and once we put this value, I need to click on the run again, and see if the column will converge or not. Yes, it converged. Okay, with this information, it converged. So you see, by providing any of the extra information, the degree of freedom here now it says 0, and it can convert. Or even if you don't have this, you can just add any other specification that is available to you, and you will be able to converge the column. Once the column is converged, okay. Once the column is converged, you can see the performance, for example, go to the specification, for example, or let's say to the parameters tab, you can see here the stage-wise, each stage, the temperature, pressure, and the liquid and the vapor. You can see the plots here. And you can also see the estimates, for example, and the efficiency of the tray. Okay. You can also see many other information. There is also something called internal. Now, I know I'm solving a random example right now, but you can click on the internals from here. And in the internals, you can basically do the detailed designing. And for example, when I click on add new button, I'll see a new design. So you see, I can choose that it's interactive tray sizing. I have a tray column. You can choose a tray column, or let's say a packed column, depending upon the nature of the column. Let's say we have a tray column, and the type of tray that we are using is, for example, bubble cap. Okay, and the number of passes is 1 in the bubble cap. And you can click on view and go into detailed design for the bubble cap tray. But in this case, I will not go into details, but because we don't have the information. But you can, I'm sorry, just need to get rid of these things, but I really don't know how to do that. Anyhow, you can do the sizing for these bubble cap trays. This information, or is the geometry and all this design, you can do it. Okay, if you have the information available. So let me delete it. It is not needed at this time, but you can do it if you have the required information. So this is about distillation column. Okay. And now the next thing maybe is we can do, let's say, simulation. Let me save this file. The next thing that we can do is simulation of a heat exchanger, for example. Okay. We can go to heat transfer, and let us say we create we take a heat exchanger and we create here heat exchanger. Now you can see that the icon for the heater and heat exchanger is the same. I can change it just from aesthetic point of view. You can right click on it and click on change icon, and you can choose the icon that you like. For example, this or this. So this is now this is an heat exchanger. Let us create try to solve it. Let's say we create let's we have a tube in, for example. Then we have the shell inlet. It's a shell and tube exchanger. So shell in. We have tube out, and we have shell out. Okay. Now, as you know, once I do this, I'll create the streams. I can go to the editing streams manually, or I can go to the worksheet and edit each stream. Let's say from the shell side, from the tubes, or we need to do the composition also. So let me do it manually here. So let us say on the tube side, we keep, for example, methanol and acetic acid mixture. Okay. So 50-50, for example, or let's say so 0.3 methanol and 0.7 acetic acid or mole fraction. Okay. And let us say we want to conditions. Let's say we want to keep it as saturated vapor, for example, at a certain temperature. So when I put 150, the pressure will be very high. It's around 3.28 bar. Okay. And let me put the flow rate as, or the mass flow rate. Let me put the mass flow rate as 200 kg per hour. So I have a tube inlet stream, and it is saturated vapor. Yeah, although we should not put saturated vapor in the tube side, but it's just an example. And the shell in, let's say we want to use cooling water. Okay. So it's a cooling water. Let's say we put the temperature around 20 degrees Celsius. The pressure is, let's say, 2 bar, and the flow rate is, let's say, around 180 kg per hour. Okay, and the composition is pure water. So I'll put 1 here, press enter, and okay. So now this stream is also solved. And you see, I have tube in and shell in defined, but still the heat exchanger is not solved because I need to provide the information about in the design type about the parameters like the pressure drops and these things. And also I need to provide either the duty or I need to provide one of the condition for the outlet. Okay. So in this case, if I go to the worksheet, let us say I want this tube inside to be condensed. So from everything is same. Let's only from saturated vapor, it changes to saturated liquid. So I'll press 0 here. And still I need to provide the pressure, for example. And the pressure, let's say, if you provide the pressure drop from here, there should be a pressure drop here, parameters. Yes, here. The specified the pressure drop for shell side, let us put is 10. And for the tube side, let us put is 10 also. As soon as I do it, I think it should solve the system. Yes, it did. Okay. And if you go to the worksheet, you will see that when we want to condense the vapor from saturated vapor to saturated liquid, the water temperature will increase from 20 degrees Celsius to 118. Okay. And pressure drop is the same. Okay, 10, 10, and 10. So you see that pressure is decreased. And you can go to the performance, and you can see the plots for the heat exchanger. If you like to the temperature, this is the temperature and pressure, but you can see the enthalpy plots, for example, or the heat flow. And these. Another thing is, if you look at the heat exchanger here, this is simple endpoint method. This is just basically, you can say like energy balance, and it will give you the very basic information. Also, I can alter the number of tube passes and the shell passes from here. I can have, like, for example, 2 tube or even more than that tube passes, the shell passes, and I can choose whether it is counter current or co-current. Also, I can choose an E-type or F-type of exchanger. That are the details, maybe you can know about it. Just like the distillation column, if you go to specification, maybe if you don't know the temperature, for example, of the exit stream, you may know, for example, the value of UA, or maybe you know the heat balance for this system, or you can add any other specification. For example, you know delta T, or you know the minimum approach, or you know LMTD value, any of these parameters that you can put it and it will solve the system for you. Okay, you can also add the fouling factor or something. This information can be available here. So not just the temperatures, you can also add the other specification and solve your system. For example, let's say here UA is already used, but let's say if you know the minimum approach temperature, you can utilize that, and it will calculate for you the exit temperatures. Now, if you have done this already and you want to go to rigorous design, then you can click on size exchanger button. Okay, the size exchanger button will basically takes you to another, just like the discussion column, to another detailed design of heat exchanger. If I click on size exchanger, I can use size interactively. Size interactively means I'll be able to use myself the options change it. Auto sizing will do the auto thing for you. So I click on the convert. It will take a while, and it will take you to a new setup menu where you can basically design the heat exchanger by providing the details. And if, for example, I can, you are aware of the standard of this is TEMA, is basically Tubular Exchanger Manufacturing Association, and they have different types of standards. For example, your exchanger is a B type, PEC means any, for example, it's bonnet, or a C means integral, any of the structures. So you need to look at your exchanger, which type of exchanger you want. Okay, for example, I don't know right now, I have no idea, but let's say we choose it to be the B type, the default one. E means one single pass, F means two shell pass, G means split flow, and so on. So let us say we put it as F, and for the M bonnets and integral. Let us say we put as the default one, M. Now here we need to provide the tube's diameter and the pitch. For example, we want rectangular or square pitch and these things. So let us say put it these. The tubes are in baffle window and these things. So when you provide all the informations, and then you click on the size, it will try to solve it, and then you see you get the design. Although it's this is the stream temperatures, but because we are just using random values, so I don't think whatever we are getting will make sense. So it gives you an estimated cost. It also gives you the detailed diagram. It also gives you any warning that you have. So it says the warning that is here, it says you did not input any fouling resistance. Okay. So the fouling resistance there is, I think, in the process tab. Yes, here we need to add the process conditions. Okay. And also there is a place to add the fouling factor. So once you do that, you will be able to size the exchanger in detail. Yes, cancel it. Okay, click on this and close it. Let me save it. So let me pause the recording. So we are done with the distillation column, most important mixer, and let us do just one more example about the reactors, and then I think I can conclude this this lecture. So I have one file ready already, since we already have spent 1.5 hours. So I want to keep it a little bit concise. So I have one file ready. It's about I'll show this to you. It's about the propylene glycol production. Okay, and we are using the components propylene oxide, and it reacts with water. We have a CSTR reactor here, and then we get some products, and the products are then separated from the reactor. Okay. So let us see to the properties environment, and as usual, first of all, I need to define the components. This is the diols mean the glycol, and this is 1,2,3 oxide is the propylene oxide, and we have water. Okay, I added those components, and then I went to the fluid package. In the fluid package, we have added the unique fluid package, and in the reaction tab, this is important. We have a set one of the reaction. Inside set one, we have a reaction one. And reaction one is basically, if you look here, we have the propylene oxide and water. These coefficients are -1, -1. They both react to produce 1 mole of this, react with 1 mole of water to produce 1 mole of propylene glycol. Okay. And once we do that, since it is a conversion reaction, so we need to add the values for the A and the E. This is the activation energy, and this is the value of the frequency factor. Okay, so once we add these informations, we just click on attach to the fluid package, and it's already ready because it is already attached to the fluid package. If I click on detach, it will be removed. Okay, and then I can go to the simulation environment. In the simulation environment, I have two streams. One is the propylene oxide, and you can see it is at 23 degrees Celsius, and the pressure is 1.15 bar, and this is the molar flow rate. Okay, and we have the water flow rate. Water stream, which is at this condition, temperature, pressure, and the flow rate. Okay, the composition is pure water. The mole fraction is 1. Similarly, here the mole fraction should be 1 because pure. Now we mix it in a mixer, and then after mixing it, we send it to the reactor. So the reactor is a CSTR. We can see it we can choose it from the model platelet. Okay. You double click on the CSTR again in the design tab. You need to add 3 streams. Okay. So first one is the stream, which is to the reactor. This is our inlet, and we have two streams. One is the vapor part, and one is the liquid part. Now, sometimes in Hysys, in certain unit operation, these streams are required, even if you don't have any product. And for example, in this case, we don't have any vapor product, but still we have to create a stream. So you can call it as a dummy stream. It will not have anything, but still you need to create it. Okay. So we have to the reactor one stream, and then a liquid product and a coolant also, because we want to maintain the products at, let's say, for example, the reaction at certain conditions, at certain temperature. You see the liquid part, I want to keep it at 75. That's why I want to provide a certain heating duty. Now, also for CSTR or conversion reaction, you need to provide the volume. And the conversion reaction or the conversion reactor, you just need to specify the conversion and that's it. You don't need to have the volume for the reactor. However, in Hysys and conversion reactor like CSTR, sorry, in the kinetic reactor like CSTR or plug flow reactor, you need to provide this information like the liquid volume, how much, and the liquid volume, the percent of the reactor, or the percentage of the liquid volume, and the liquid volume is these values usually are by default, but the volume of the reactor is important and you need to provide it. Okay. Then once you define these things, the streams, attach the streams, the next thing is you need to go to the reaction and attach a reaction set. Okay, or you can see from here, you can attach a reaction set. As soon as you attach the reaction set and everything is defined, then you will be able to solve the system and it will turn green. And you can see the result from here. The conversion is actual conversion is 99.57 or 100% of the reactant. And you can see the volume of the reactor is 7.929, the diameter, and these are calculated already. And you can see from the worksheet, if I change the temperature from here, the product temperature, if I make it 50, everything will change. You see the conversion slightly is changed. It became 68, the actual conversion and the extent. And you can see, if you look at the ratings, yeah, I think this will not change, but mainly the heat duty will change. Okay, from here. So I can change it back to 75 and keep it as it is. Okay. And the product vapor, if you look at the composition, there is nothing or very minimal amount of vapors. Okay. And let us see, what do we have in this case? Yeah, you see the molar flow rate is 0 for the vapor. So there is nothing in the vapor. However, in the liquid. So when we get the liquid, we then send it to the liquid product to distillation column. Okay. Like we discussed before. So first we need to use the shortcut column to get the minimum number of stages or the number of stages, and then the reflux ratio on these things. So we defined our product liquid is going into a column, and we get overhead and recycle product and the boiler duty glycol, the liquid product, and so and so. These things. And then in the monitor tab again, you see we need to specify a composition. Like for example, we have the reflux ratio, but in this case we don't have the overhead product or the reflux or distillate, but we have the fraction of water in the, if you double click on this, it is basically a specification that we have added, and it's water fraction in the reboiler and small fraction, and it is 0.005. So when you add that and you click on run, it will basically solve the problem, and you can see the pressure and temperature profile or the flow rate flow profiles in here. So once you solve the column, it is you get an overhead product. Okay, this stream basically contains some water and mainly water, and the recycled product we have in the composition we have mainly water. And let us see the flow rates. We can add a recycled stream from here. It's 4921, and this is yeah, this is very small product. This is the main product, and we have the glycol here at 68.38 mole per hour. Now let us see, for example, from here we want to, let's say, recycle some of let's say this one, let's say for example the water stream, that maybe we want to add a recycle to it. So for that purpose we need to, let me just take out the model platelet again. If the model platelet is not shown here, you can go to flow sheet and click on the object platelet. Sorry, click on view, and then it's a model platelet. So from here, if I want to recycle the stream, let's say, so this thing is really bothering me a lot. So if I look here, I can see the recycle icon here. I can take out the recycle icon and place it here, for example. Now I have added a recycle block. Okay. If I double click on the recycle block, I need to add to it, for example, the inlet stream. I want to add the recycle product to the recycle. Okay. So this is my recycle. I'll say to the outlet stream from the cycle should be to the mixer. Okay. That's all. And It is solved, but not yet. I want to add this water to this mixer, okay, the recycle one. So I'll take this mixer, double click on it, simply double click on the mixer and click on the design. And I have two things already, two streams already added to it, and I'll add to mix also another stream. Column liquid, yeah, because things are messed up because now we have a lot of water added to the system. Okay, it is solved, although, but I was worried about this thing because now the water flow rate is too high. The session column internal configures have changed. Yeah, we have changed everything because now we are adding a lot of water again, 3.54 kilomole per hour to system. And if you look here, it will change even our conversion, for example, to the reaction, and the result is here, and the glycol production is still the same. But although it is solved, the recycle block, let me check. No, it is not solved yet, you see, because I can see the yellow color on the boundary here. So it means it is not solved. Let me click on it, and once I click, I can click on continue to continue the iterations. And in the next phase of iteration, it will be able to solve it. And we have conversion now. Now I think we should slightly, okay, it's not changing anyhow. So this is all any, for example, this is how you add a recycle block. You can also add the adjust. The adjust is basically used to select a variable, an object, and then you can adjust. For example, let me select the adjust, for example, let's say in the mixer. mm, wait, product molar flow rate, for example, and I can select the molar flow rate, okay, in the mixer, and I want it to be, let's say, at certain ratio of another thing, any. So for example, if I want, now if you look at that, just basically it will take the product of this mixer, okay, the molar flow rate, and adjust it to according to some ratio of here. You can provide a value or you can provide a target value here. I don't have any information, any data to work on it right now, but basically the adjust parameter is used to adjust one stream to another. Okay, let me delete it. So for example, I want the temperature of this stream, for example, it is right now 99, okay, 99, but I want to change it to, let's say, 120 by changing the temperature, for example, here, okay. So what the adjust parameter can do is, or I want the flow rate to be a certain composition, or this stream to be of certain composition by varying the flow rate of this stream. So I can use the adjust for it. Similarly, there is another one, set. So set is a multiplier, like for example, I have two streams, the propylene oxide and water, and I want them to be in certain ratio. So you can use a linear relationship, and let's say it is better when it is used when you have like a certain ratio of the components you are feeding to the reactor and these things. So you can use it, and you can add a connection by selecting a variable. For selecting the variable, I can go to the mixer, okay, and I can select the product mole flow rate from the mixer, and the object. Uh, let me select the mole flow rate of propylene oxide. Let's say propylene oxide. Okay, I want to select the mole flow rate, molar flow. Okay, select, and the object. I want to, let's say, the water flow rate. Okay, it's giving me a consistency error because we already have specified the water flow rate and these things, so that's why it will give us consistency error. Anyhow, let me just delete it. Now there is one thing that I told you in the start, and you'll see it now. You see, when I receive the consistency error, the solver has gone to hold now by default. And now even if I delete this, the set operations, Hysys will not keep the solution, So when I need to change it to active, and when I change it to active, it is solved now. We need to do some changes in the column again, because we, after adding the recycle stream, there are some things have been changed, especially in the internals. Uh, but we can delete these internals so that that's all. And you can click on the workbook. Okay, so you can in the workbook basically uh, it shows you all the streams, like for example propylene oxide, water, and then to the reactor, and all the things that is available in the all the properties. For example, let me just close this. You have the vapor fraction, the temperature, pressure, molar flow rate. All these things are available in the flow sheet. If any of the parameter is not available and you want to add to it, okay, let's say for example I want to add something, viscosity or CP to this workbook, I can click on the setup icon and I can add a variable and choose the variable. For example, if I search for CP by CV or heat capacity, let me search for heat capacity. Yeah, so it's mass heat capacity or molar heat capacity, and click. Yeah, so heat capacity, I click on done, and it will show me the heat capacity also now. And this heat capacity is already now available for all the streams. Similarly, you can go to the composition tab. You can also go to the energy streams. All the energy streams will be shown here. Similarly to unit operations, so we have our mixer, we have a CSTR, and you can change things also from here. And yeah, you can double click on it. You want to change something or edit or any information, you can do it. Similarly, for the material stream in these, you can change anything. And for example, if I change the molar flow rate of this to, for example, 80, it will change all the calculations, everything. So it gives you a summary of all the flow sheet, and you can do any editing from here. Okay, you can also then print the workbook or send it to Excel, I believe. Yeah, export it to Excel, and you can print it also from here. Okay, let me close this. And let me show you another thing, which is, for example, maybe the case study tool. Okay, so the case study tool is also an important. I will not apply it to these things because it will maybe things will be messed up. But we can add a simple material stream. Okay, let me just copy the propylene oxide stream, for example. Let me copy it and let me paste it. Okay, now for the case study, you can click on the case study here, and the case studies I can let's say double click on this. This is my case study, and you can add a case. Okay, now we already have one case study here, so we can see, for example, you can in the case study you want to study the effect of one variable, let's say, or an independent variable on the dependent variable. For example, you can study the effect of volume on the conversion. You can study the effect of temperature on the conversion, and these things. So we have one, let's say, CSTR volume, and the current value is 7.9. You can click on variable manager and add a variable. And if you can click on find variable, and you can select the object type, like, or let's say you can go to the column and select something, or you can go to the object type and CSTR from here. And from CSTR, I can select the duty or the volume or these things, any of the parameters for the CSTR, or let's say even for a heat exchanger. Okay, and the other thing that I want to see is conversion. Okay, so again I can go to the variable manager, and for the CSTR I can search for the conversion and take it as my dependent variable. So this is an independent variable and a dependent variable, and then the case study setup, I want to vary the volume from 2.5 to 12 with a step size of 0.5 to see the effect. So when I click on run, after running, I can click on results, or I can see the plots. So in the plots, you can see that basically when we increase the volume, the conversion is increasing. Then, for example, when the volume is 2, the conversion is less than 98, or let's say around here. You can click on it and it will tell you the value. When the volume is 2.5, the conversion is 98, and with increasing the volume, the conversion is increasing. And around 6 meter cube, we get the 100% conversion. Okay, so from here we can think that, okay, we don't need 7 meter cube or more than that volume, because at 6 meter cube we are already getting the full conversion. Okay, similarly you can have another case study. Let's say you can click on add, And for example, I want to find the variable, and let's say the independent variable in the CSTR. Let's say I want to see the effect of temperature. Okay, the ambient temperature or the bulk liquid temperature. Okay, let's say the bulk liquid temperature. Click done, and right now it is 75. Remember, we're drawing the products at 75, and I want to find the variable and see CSTR, and I want to see the effect of temperature on conversion. Yes. And click done. Now I can go to the case study setup. I can vary the temperature, let's say from 30 to 75 with a step size of, let's say, 2.5. Okay. And once I put the information, I can click on run. Yeah, when it is solved, the results are here and we can see the plot. Okay. Good. So it is 175, and it varies from 30 to 75 with a step size of 2.5, and then the results are here. So it is the temperature is start at 30 and 75. Why is it not showing? Okay, it's starting at 70, and then it's showing us one result. I don't know why. Let me just put it again. So it's not going below 75. I think
Maybe because of the current value.
yes, because of the current value. Yes, this is what I assume. But anyhow, you can try to explore these and just try to come up with other things. Let us see if we can do a case study for water, for example. I can go to variable manager, and there is a stream known as P or oxy. We created an extra stream, remember? And I want to see the effect of let's say temperature, for example. Can search for temperature and click done. And I want to see the effect of temperature on the same stream for the molar volume, for example. Just a very basic thing. When I search for the molar volume and click done, the case study setup, I want to vary the temperature from 20 to 60 and click on run. But if this stream is a liquid, you will not see any much change, but let us see. Yeah, because it's a liquid, I believe, that's why. But still we can see. Okay, so yeah, it changed from, I think at some point it is changing from almost small value, and then it is the volume, sorry. Yes, so the volume has increased. 40 and above, I think the volume is not increased because maybe the phase change has already occurred. Okay, so the case studies tool is already also very important. For example, you can also see the effect of this input flow rate of this molar flow rate of this on the conversion of the glycol or the any other conditions on the conversion in the reactor and so on and so. Okay, I think that's all from my side. And I forgot to tell you in the start that we have already one manual available in the department. You can download this manual for you. It's for ASPEN Hysys, and you can see it's from chapter 1 is about the introduction, and then we have from introduction then the chapter about the simulation of selection of thermodynamics package and so and so. So all the heaters and these things are all covered inside these with the proper screenshots and everything. So that will be also very useful for you, especially the chapter about the reactors and the the logical operators. So these recycle them, these things you can do it. We have some case studies examples also. You can do that and get a hand on practice on Hysys. So that's all from my side. You can find tons of material already on Hysys. There are some very nice YouTube channels with very good examples. You can also explore them. And I think once you have this basic information and how to start and how to create a case file and these things, then it will be easier for you to learn whatever available on the internet. So that's all from my side. Please let me know if you have any other questions. Otherwise, we will just end the class.
Doctor, I have a question.
Yes, please.
Do we need a license